Hey everyone, and welcome to this explainer. Now, we all know about the absolute heavyweights of the bloodstream, right? The red and white blood cells. But today, we're zooming way in. We're looking at the invisible, microscopic workforce that operates entirely in the background, the plasma proteins.
Here is our roadmap for today. We'll kick things off with the liquid of life, then meet the major players. After that, we'll look at the acute phase responders, check out the body's defenders, explore separation and electrophoresis, and finally, wrap up with when plasma proteins fail.
All right, let's jump right into Section 1, the liquid of life, setting the scene in the bloodstream.
So within the liquid highway of our blood plasma, which, by the way, makes up roughly 55 to 60% of your total blood volume, we find our main subjects, plasma proteins. Biologically speaking, they are soluble globular polymers of amino acids. But really, you can just think of them as a highly specialized workforce, acting kind of like a massive city's infrastructure. Most of them are synthesized right in your liver, and they go to work acting as cargo trucks, structural guards, and chemical messengers. But what's truly astonishing here is the sheer scale of this operation. There are over 300 different proteins circulating in your plasma right this very second. Together, they make up about 4% of your body's total protein, and practically every single one of them, with the notable exception of albumin, is a complex glycoprotein.
Moving right along to Section 2, meet the major players, albumin and the globulins.
While there are over 300 types of these proteins, they definitely fall into a strict hierarchy. If you look at the breakdown, albumin is the undisputed heavyweight champion of the plasma, hogging roughly 52 to 58% of the relative space. The rest of that space is divided up among the globulin fractions, alpha-1, alpha-2, beta, and gamma globulins. And each of those fractions contains their own highly specialized proteins, like antitrypsin, transferrin, and our antibodies.
Since albumin takes up so much real estate, we definitely need to look a bit closer at it. It's synthesized entirely by the liver, and you can really think of it as the heavy lifter and the pressure regulator of the blood. It has a 20-day lifespan dedicated to a really massive job, maintaining 80% of your plasma's oncotic pressure. Basically, that just means it keeps water inside your blood vessels instead of letting it leak out into your tissues. Plus, it acts as the ultimate cargo truck. It securely binds and transports fatty acids, calcium, and incredibly, just a single albumin molecule can carry multiple different medications at the exact same time. Pretty wild, right?
That brings us to Section 3, the acute phase responders, dynamic shifts in emergencies. So, what happens when trauma, an infection, or serious inflammation strikes? Well, we see a really dynamic trade-off. We have what are called positive acute phase proteins, like C-reactive protein and haptoglobin, which rapidly increase to fight off the injury or infection. But to actually fuel this massive scale-up, the body purposefully drops the production of negative acute phase proteins, like our heavy lifter albumin and transferrin. It's an incredibly elegant, immediate resource reallocation. The body is literally sacrificing normal transport and pressure maintenance just to free up the amino acids it desperately needs to pump out emergency first responders. Next up, Section 4, the body's defenders, the immunoglobulins. As the literal military force of the bloodstream, these defenders have a super unique architecture. You'll notice the classic Y shape. All immunoglobulin molecules consist of two identical heavy chains and two identical light chains, and they're tightly held together by these things called disulfide bridges. At the very tips of that Y are the hypervariable regions. These are custom-designed, highly specific binding sites meant to perfectly latch onto specific foreign invaders, which we call antigens. Now, there are 5 main classes of these defenders. You have the massive, star-shaped IgM, which is actually composed of 5 of those Y-shaped units, and that's essentially the first heavily armed responder to attack a microorganism. Then you have IgG, which is the single-unit monomer that makes up about 80% of your antibodies. IgG is so vital that it can actually cross the placenta to provide immune protection straight from a mother to her developing fetus. All right, Section 5, separation and electrophoresis, decoding the fingerprint.
So we know what these proteins do, right? But how do pathologists actually catch them in the act and measure such an incredibly complex mixture of totally invisible molecules? The answer lies in a brilliant analytical technique called electrophoresis. The process itself is wonderfully simple in concept. Step 1. You place the plasma sample on a specialized medium and apply an electric field. Step 2, because these proteins all have different electrical charges and physical sizes, they get pulled through the field at totally different speeds. And step 3,
This physical race separates the complex mixture into 5 distinct, broad fractions. It essentially forces the proteins to line up by their size and charge, creating what is basically a molecular mugshot.
This physical race builds a perfectly readable landscape for doctors. Over on one end, closest to the positive charge, we have the massive, towering peak of albumin, which totally makes sense, right, given that it's the most abundant. As we move across the graph, we see the smaller, gentle, rolling hills of the alpha-1, alpha-2, and beta-globulins. And finally, on the far end, we have a broad, smooth bump that represents all our varied gamma-globulin antibodies. This is exactly what a healthy, normal protein fingerprint looks like.
And that brings us to our final part, Section 6, when plasma proteins fail, reading the medical blueprint.
So what happens to that beautiful, rolling landscape of a graph when these proteins disappear, mutate, or multiply uncontrollably? Well, if you compare the normal control reference pattern to a pattern showing a monoclonal increase, the difference is absolutely staggering. You get this massive, terrifying spike towering over everything in the gamma region. And that spike indicates a malignant proliferation. Basically, a single clone of B cells has gone completely rogue and is just continuously pumping out identical, entirely useless antibodies.
That single, dense band on the graph is often called an M protein or a paraprotein. When a pathologist sees that spike, it is the glaring fingerprint of serious immunoproliferative disorders. We're talking about conditions like multiple myeloma, B-cell non-Hodgkin lymphomas, or Waldenstrom's macroglobulinemia, which is where those massive IgM pentamers make the blood incredibly viscous and thick. It is a really striking visual of the body's defenders multiplying wildly out of control.
In contrast to that sharp spike, take a look at what happens with liver cirrhosis. The distinct valley between the beta and gamma globulins completely disappears. It creates what pathologists call a beta-gamma bridge. This blurring of the lines happens because the severely damaged liver simply can't synthesize normal proteins properly anymore, which completely disrupts the entire delicate balance of the bloodstream. But you know, sometimes the danger isn't an excess of proteins, it's an absence of them. Take alpha-1 antitrypsin, for example. This protein's job is to neutralize destructive enzymes released by our own immune cells. In a genetic condition called alpha-1 antitrypsin deficiency, the protein is manufactured defectively and just gets trapped right inside the liver. Because it never actually reaches the blood, the alpha-1 band completely disappears from the electrophoresis graph. The clinical result? Well, the trapped protein causes childhood liver cirrhosis, and without its protective presence in the blood, young adults can develop severe pulmonary emphysema as enzymes literally digest their unprotected lung tissue.
As the source material highlights with absolute, perfect clarity, organic diseases may result when their concentration in plasma is altered. Every single peak and valley in that electric separation tells a really critical story. Any shift in this delicate protein balance provides an immediate, direct window into the presence of an underlying organic disease, whether it's an inflammatory emergency, a failing liver, or a hidden malignancy.
It's an absolutely incredible system of transport, defense, and emergency response, and it's all happening invisibly inside you every single second. It really makes you wonder, if you were to undergo electrophoresis and take a molecular mugshot of your own blood today, what fascinating story would your plasma proteins reveal? Thank you so much for joining me on this journey through the liquid of life. Keep learning, and I'll catch you on the next explainer.